Hello students, welcome to today's session. Today we are going to discuss about next part of electrostatics, that is electric potential energy. So generally if you are thinking about a potential energy is nothing but the energy possessed by the body by virtue of its position. So generally we have three types of potential energies: gravitational potential energy, electrostatic potential energy, and elastic potential energy. Gravitational potential energy we will study in gravitational topic, and elastic potential energy we are getting in solids and as well as the properties of solids wherever we have their elastic potential energy. And here electrostatic potential energy. First of all, what is the potentiality? What is the potential? Means due to the position, if the particle is gaining energy, that energy is stored in the form of potential energy. For example, if you are considering a small stone if you are dropping from a 1 meter of height, how much it creates the damage? Very less. The same object you are taking to 10 meters or 100 meters, if you are dropping, then that may create the damage, because when which is at 1 meter, that position is 1 meter from the ground. When we are taking 100 meters, 100 meter position, that position gives the energy to the particle. The position gives the energy to the particle. That energy is stored in the form of potential energy. So here we are going to discuss about what kind of potential energy is having the charges. What kind of potential energy is having the charges? Generally, if you are thinking about, if you want to swim against the water flow, that is difficult, or else is it along the direction of the water flow? Yes, obviously it is difficult to swim opposite to the direction of the water flow. Means nothing but the water flow opposes you, at the same time you have to moving in the direction of opposition. So then only you have maximum potentiality. That potentiality only that gives the potential energy to you. The same way here we have placed one positively charged body. Positively charged. There is a positive charge. Generally, what is the direction of the electric field for the positive charge? The direction of the electric field is away from the positive charge. Wherever you can take away from the positive charge. Now, you try to bring another positive charge towards it. So, actually, which kind of means this is, you can take a source charge Q, and you want to take a small charge, test charge, small Q naught. If you want to move this charge towards it, you need to do some work. Yes or no? Yes, compulsory we need to do some work, because here electric field is acting in this direction. You need to move this charge in this way. Means nothing but you want to swim opposite to the direction of the flow. That means you need to do some work. So here, see here. For example, here I am considering the situation, we are moving the charge from point B to point A. Means this charge I am moving from the point B to point A. So when which is at point B, means that is somewhat far distance, that is having somewhat less. When which is already I told you, whenever it is nearer, there is having more field strength, and far away from the charge, less field strength. So here we have some less field strength, but when we are coming towards that, the field strength is increases. That means you need to struggle also, you need to apply the more force also. For example, to move it, you are applying the force in this kind. That force we can name as external force. Which force? That external force. And also the electrostatic force is acting in which direction? Opposite to the direction of the flow. This is the direction of the electrostatic force. Why the electrostatic force direction is this? Simply that is the direction of the electric field, that is only the direction of the electrostatic force also. So now here I am considering the position A is at a point RA, and the position B is at a point RB. So total from there to there. So now we are displacing the charged particle from RB to RA, means it is having some displacement. Force into displacement, work done. Here you can observe what is the direction of the external force. The direction of the external force is this. What is the direction of the displacement? This force, external force and direction of the displacement both are same. When external force and direction of the displacement are same, so displacement and external force having same direction, then the force should be positive. Work done by the external force is positive. But what about the work done by the electrostatic force? See here, what is the direction of the electrostatic force? This is the direction of the electrostatic force. What is the direction of the displacement? Opposite. That means the work done by the electrostatic force is equal to work done from where to where you are doing the work, from A to B, which is equal to minus, or if you are taking plus, F external into dr. Why plus? External force is acting in this side. But what about the electrostatic force? Electrostatic force is acting opposite side. So then A to B, nothing but minus F electrostatics into dr. Why this negative? Here electrostatic force direction is this, and the direction of the displacement is opposite to the direction of the electrostatic force. When force and displacement are opposite to each other, then what happened? The work done should be negative. Force and displacement in the same direction. Work done positive. Here, see here. So what we are taking, just you can take integration on both sides. So then you can get the work done from where to where? Then A to B. Then minus integral. So Fe means electrostatic force between the two charged particles. At its separation, you can consider the separation is somewhere R. So that is 1 by 4 pi epsilon naught Q naught upon R square. So K 1 by 4 pi epsilon here I am writing as K Q naught upon R square into dr. And what are the limits? From where to where we are moving? From RB to RA. From RB to RA we are moving. RB to RA. So now simply take the integration. What we are getting? Work done from A to B, and K minus K Q naught is the constant function, and integral 1 by R square. Integral 1 by R square integration is goes to minus 1 by R. Minus 1 by R. The limits are RB to RA. So then the work done is equal to, simply we can able to write from A to B, that is equal to minus K Q naught, upper limit minus 1 by RA, minus of minus plus 1 by RB. You can take minus inside, then you what we are getting, the work done from A to B is equal to K Q naught 1 by RA minus 1 by RB, 1 by RA minus 1 by RB. So this is the actually work done by the gravitational force. Work done by the gravitational force while moving from A to B. Actually, this electrostatic force is a conservative force. Electrostatic force is a conservative force. The work done by the conservative force, anywhere you can take work done by conservative force, is stored in the form of work done by the conservative force is stored in the form of negative potential energy. Negative potential energy means we are taking minus delta U. Minus delta U. So the work done means if you are taking that minus delta U means UA minus UB. UA minus UB, and that's the work done is equal to, we can able to write UA minus UB, and the work done from A to B we can able to write UB minus UA. UB minus UA. So you can observe here, if you are taking this work done as a negative function only, I will keep the value like this only, means for example, if I am taking this work done UA minus UB, instead of that you can keep this like this only. That means UA minus UB is equal to minus of work done from A to B. minus of work done from A to B. Means the negative work done is C here. Which work is done by the electrostatic force? Negative work. But what about the potential energy? Increasing potential energy. Increasing potential energy. So let's see here. The potential energy expression you can able to write here. The simply U is equal to UA minus UB is equal to minus of work done from A to B. Minus of work done from A to B. If you are writing this expression, the minus of work done from A to B means this minus you can send here. So that means you are getting here this work done means I am writing here minus of work done from A to B is equal to UA minus UB. And now this value what we can able to take minus K Q1 Q0 by 1 by RB minus 1 by RA. 1 by RB minus 1 by RA is equal to UA minus UB. This is the generally the potential energy expression from A to B. The potential energy expression from A to B. So if you want to take the potential energy at point R, if you want to take the potential energy at point R, means it is at a distance R, then the potential energy of the particle is going to be, the potential energy of the particle is going to be, means you can multiply minus inside, then what is happening? RA minus RB only you are getting. The potential energy UA is equal to what we can able to take? K into Q0 upon RA. UB is equal to Q0 upon RB. Whereas if you are taking at R, means if B is equal to infinity, take B is equal to infinity distance, and RA is equal to take A. RA is equal to take R, and B is equal to you can take infinity. So then what we are getting that? Just to put these values. If you put these values, then UA minus UB is equal to minus K Q0 by 1 by infinity minus 1 by R minus minus plus. So then UA is equal to UA minus U at infinity is equal to K Q0 upon R. Means wherever you are considering the potential energy, which is going to be simply K Q0 upon R. What is the potential energy is there of the charged particle when we are taking from infinity to a point R? The potential energy is K Q0 upon R. That is the potential energy. You can observe here, if we are moving the charged particle towards, the potential energy of the particle increases, but work done is negative. Negative work done, increasing potential energy. So let's see here, we will see the electrostatic potential energy between two charges. Any two charges you can consider. Here I am considering one positive charge and as well as one negative charge. What is the electrostatic potential energy between them? So here if you are taking a positive charge Q and another charge is a minus Q0 or separated at a distance R. Generally, which kind of force is existing between them? Means these two charges are attracting each other. So these two charges are attracting each other. So then attraction takes place and the potential energy is equal to minus K Q0 upon R. Why? This is at a separated a distance R and the magnitude of the charge Q0 by R, and also this charge is having less potential energy because it is attracted by it. In case if you want to move the charge in this side, the potential energy of the charged particle is increases. If the charged particle is moving towards here, then potential is decreases, potential energy decreases. So between two positive, one negative and one positive charge, the potential energy is minus Q0 upon R. Whereas you can consider two positive charges are separated by a distance R. Then what about the potential energy between them? Actually here which kind of force is existing between them? Repulsion. If you are trying to bring the particle towards it, what happened? you need to do the more work, means the potential energy of the particle increases, right? So here, which kind of force? That gives repulsion, and the potential energy is equal to Q0 upon R. Q0 upon R. So this is the potential energy between two positive charges, one positive charge and one negative charge. In case if you consider two negative charges also, you are getting same kind of potential energy. Let's see, we'll take between three charges. Potential energy between three charges. Which charges we'll consider? Positive or negative? Yes, anything you can take. For example, I am considering three charges, plus Q1 minus Q2 and plus Q3, or else plus Q2 minus Q3. Take like this. And the distance between from here to here is R1, R2 and as well as R3. Now what is the total potential energy? See here, the total potential energy between these two particles I am taking as U1. U1 is equal to K 1 by 4 pi epsilon. K is nothing but Q1 Q2 upon R1. And potential energy between these two charges, one positive and one negative, how much? U2 is equal to minus K Q2 Q3 upon R2. Why minus? These two are one positive, another one is negative. So that's why minus K Q2 Q3 upon R2. Next U3 means between these two again minus K Q1 Q3 upon R3. Now the total potential energy of the system, U is equal to U1 plus U2 plus U3, that is equal to K Q1 Q2 upon R1 minus K Q2 Q3 upon R2 minus K Q3 Q1 upon R3. So like that, if you are getting, in case if all are identical charges and identical distance, same distance, we'll check. If Q1 is equal to Q2 is equal to Q3, if R1 is equal to R2 is equal to R3, and Q1 is equal to Q2 is equal to Q3, minus, no change in that 3 value, magnitudally same, nothing but Q1 is equal to plus Q, Q2 is equal to plus Q, Q3 is equal to minus Q. If you put the values in this expression, what we are getting? Let's see what we are getting. The total potential energy U is equal to K Q square upon R minus K Q square upon R minus K Q square upon R. Then the total potential energy of the system is minus, these two will be cancelled out, then minus K Q square upon R, minus K Q square upon R. If all are plus, if even this is also plus, then what about the potential energy? The potential energy should be 3K Q square by R. So see that also. If Q1 is equal to Q, Q2 also Q, Q3 also Q. So then what happened? The potential energy K Q square by R. Yes. This also K Q square by R. Yes. This also K Q square by R. Then total potential energy is equal to 3K Q square by R plus one charge negative, so that's why we got negative potential energy, and three positive charges, then we are getting K Q square upon R. So like that we can calculate the potential energy between two charges and as well as three charges. We'll see four charges also. Okay, let's see here potential energy between four charges. I am considering four charges. What are the possibilities? So see here, first of all, Q1, Q2, Q3, Q2, Q3 and Q4. How many potential energies we are getting? See here, 1, 2, 3, 4. See here, between 1 to one potential energy. Between 1, 3, one potential energy. Between 1, 4, one potential energy. See here, what we can take here? 1, 4 charged particles. 1, 2, 3, 4. Means how many terms we are getting or how many we are getting here? Between 1 and 2 means K Q1 Q2 by R square. Between 2, 1 and 3 K Q1 Q3 by R. Next between 1 and 4. Next between 2 and 3. Between 2 and 4. Between 3 and 4. Means total how many? 1, 2, 3, 4, 5, 6. 6 number of potential energies you are getting. Total how many potential energies you can get? 6 potential energies. Between 1, 2, 1, 3, 1, 4. 2, 3, 2, 4, 3, 4. Total. Like that you are getting. So here, if it is a square, actually you can take a square. Square, that means we need to take here, this distance is R, this is also R, this is also R, this is also R, but this distance is different. How much? This is root 2 R, this is also root 2 R. Then how many potential energies you are getting? U1 between these two, U2 between these two, U3 between these two, U4 between these two, U5 between these two, U6 between these two. Means like that you are getting 6 terms. How many terms you are getting? 6 terms you will get. So see here, so what I am doing here, I am considering identical charges because somewhat easy to calculate. See here, U1 is equal to K Q square upon R. U2 is equal to, between these two, K Q square upon R. U3 is equal to K Q square upon R. U4 is equal to K Q square upon R. Between these two, between these two, between these two, between these. Now between these two, that's I am giving Q5 is equal to K Q square upon root 2 R. U6 K Q square upon root 2 R. Now the total potential energy is equal to, total potential energy U1 plus U2 plus U3 plus U4 plus U5 plus U6. Total potential energy. KQ square by R means total how many terms you have? 4. 4KQ square by R plus, here how many terms you have? 2KQ square by root 2R. Means this you can able to write simply root 2. So nothing but if you are taking common KQ square by R, the remaining 4 minus root 2. 4 minus root 2. So this is the total potential energy of the system. In case means, see here, for 4 particles only we got 1, 2, 3, 4, 5, 6. Like that, if 5 particles, how many? The possibility increases. 6 particles increases, 7 particles increases, n particles increases. So that's why we have a shortcut here to find number of the charged particle. How many number? It's not independent. That means simply n into n minus 1 by 2. How many terms you are getting? So n into n minus 1 2. It's a shortcut. See here how we can take n into n minus. For example, for 3 charges, 3 into 3 minus 1 by 2. How many it is you are getting? 3 only. We got 3 now already. 3 only. Take 4. 4 into 4 minus 1 by 2. 4 into 3 by 2. How many times you are getting? 6. See here. 1, 2, 3, 4, 5, 6. In case 5. 5 into 4 minus 1. Sorry. 5 minus 1. 5 minus 1 by 2 means how much you got? 5 into 4 by 2 means how many possibilities? 10 means U1, U2, U3, U4, U5, U6, U7, U8, U9, U10, but that is going very lengthy. Like that, 6, 7, 8, 9, 10, how many you have? The potential energy between the particles, we can able to solve it simply. So we'll see one more problem here. So what is the problem? 3 identical charges are placed at the 3 corners of an equilateral triangle. 3 identical charges are placed at the 3 corners of an equilateral triangle. three corners. Means you take identical charges, three corners, here plus Q, here also plus Q, here also plus Q. And what is the distance is I am taking R. Now what is the question is here, first those are fixed. Now just those are released. When those are releasing, what happened? Which kind of force is existing between them? Which kind of force is existing between them? Generally repulsion. Due to the repulsion, those charged particles are moving away from each other. When those are moving away from each other, when the distance between the charges is 2r, what about the velocity of the each charge? The distance between them is 2r. So distance is increases from r to 2r. So then what about the velocity between them? If you want to write the problem. What's the problem here? Three identical charges are placed at the three corners of an equilateral triangle. Three identical charges are placed at the three corners of equilateral triangle and released. Placed, then released. So initial distance is r. When the separation between them is 2r, when the separation between them is 2r, then what is the speed of the particle? What is the speed of the particle? So see here. Initially all are separating by distance r. Now that means they have some potential energy, initial potential energy. How much? All are identical na? Between these two, how much you have? Kq square by r. Between these two, how much you have? Kq square by r. Between these two, how much you have? Kq square by r. If you are taking total is equal to 3kq square upon r. Right? Now we are released and those are in motion. When those are separation is 2r, what is the potential energy? That potential energy I am taking U2. U2 is equal to, here between kq square upon 2r, between these two, plus kq square upon 2r, between these two, kq square upon 2r. Means again between these two, between these two, between these two. Now the total potential energy here, how much you are getting? 3kq square upon 2r. Generally here, tell me one thing, here after releasing, the potential energy of the particles increases or decreases? Potential energy of the particle increases or decreases? Yes, obviously decreases, because those are moving away from each other now. Means repulsion is decrease. The decreasing potential energy is causing the increasing potential energy from conservation of energy. From conservation of energy. What is the conservation of energy? The total potential and sum of the potential energy plus kinetic energy is equal to remains constant. Here the decreasing potential energy is equal to increasing kinetic energy. What is decreasing potential? Generally potential energy means we are writing U2 minus U1. Here potential energy decreases, so that's why you can write directly U1 minus U2 is equal to kinetic energy K2 minus K1. You are releasing from rest, so that's why that initial kinetic energy is 0. Initial potential energy is maximum, so that is equal to, actually what we are writing here, minus means you have to write U2 minus U1. Minus is going inside, then U1 minus U2 is equal to KT minus K1. U1, how much you have? 3kq square upon r minus U2 kq square by 2r. 3kq square by 2r is equal to K2 half m v square. But how many particles are there? 3 particles. So that's why you need to take 3 half m v square. One particle of kinetic energy is half m v square. Like 3 particles of kinetic energy is 3 half m v square. Now try to simplify it. How much you are getting? 3 minus 3 by 2. 3 by 2. 3 by 2 kq square upon r is equal to 3 by 2 mv square. 3 by 2, 3 by 2 gets cancelled. Then mv square, or simply v square, is equal to k q square upon rm. Then finally v is equal to under root k q square upon rm. What is k? K is nothing but 1 upon 4 pi epsilon naught q square upon rm. This is the velocity of the particle when the separation is 2r. And also you will try to get what is the velocity when the separation is 3r. Try to solve. So let's see one more problem on this electrostatic potential energy. Two charged particles having charges 1 microcoulomb and minus 1 microcoulomb, 1 microcoulomb and other one is minus 1 microcoulomb, of mass 50 grams, each held at rest, means initially both are at rest, while their separation is 2 meters, means initial separation between them is 2 meters. Now the charges are released, these two charges are released, the charges are released. Find the speed of the particles when their separation is 1 meter. When their separation is 1 meter, then what about the speed? So generally these two are unlike charges. So that's why those two are attracting each other. So let's see here, initial separation. Initially 1 coulomb charge is here and minus 1 coulomb charge is here. Right? What is the separation? Is 2 meters. Separation is 2 meters. Now just we are releasing both, and this is coming towards and this is coming here because of mutual force of attraction. So now this is that 1 microcoulomb position and this is that minus 1 microcoulomb position. So now what happened here, initially those are having much distance and now the distance is decreases, then automatically but negative charges. So there is a change in potential energy. The change in potential energy is equal to increasing kinetic energy. See here, initially when their separation is 2 meter, what is the potential energy between them? K minus, because opposite charge na, q square by r1. How much? R1 is 2 meters. Initial distance is R1. I'm taking 2 meters. Next, U2 is equal to when the separation is 1 meter. When the separation is 1 meter. This potential energy is I am considering U2. U2 is equal again minus q square upon R2. Why I am taking q square means magnitude of the charge is same, but signs are opposite, plus or minus, whatever. Now this here potential energy decreases or increases? Decreases, because those two are attracting each other. So that's why the change in potential energy is equal to change in kinetic energy. The decreasing potential energy is equal to increasing kinetic energy. Decreasing potential minus of U2 minus U1 is equal to K2 minus K1. So that is equal to U1 minus U2 is equal to K2 minus K1. Initially both are starts from rest, so that's why initial kinetic energy is equal to 0. Now see here, U1 value how much? Minus K q square upon R1. U2 value minus of minus plus K q square upon R2 is equal to 2 into half mv square. Why 2? Those two particles are there. So now this value will be cancelled. Now just put the value of R1 and R2. R1 2 meters, R2 1 meter. Nothing but k square by R2 minus k square upon R1 is equal to mv square. So k square you can take common. Then 1 by 2 minus 1. 1 by 2 minus 1. That's only na. R1 is how much? 2. Sorry. R1 is 2. R2 is 1. So 1 minus 1 by 2. 1 minus 1 by 2 is equal to mv square. So this is goes to 1 by 2. Then finally mv square is equal to kq square by 2. kq square by 2. Then v square is equal to kq square upon 2m. That means v square is equal to k value 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught q square by 2m. Just put the values. V square equal to 9 into 10 power 9, q square 1 microcoulomb is nothing but 10 power minus 12 upon 2 into 50 grams, nothing but 50 into 10 power minus 3. So see here, this minus 3 is going here, plus 3, nothing but 10 power 12, 10 power 12 will be cancelled. 10 power 12, 10 power 12 will be cancelled. So then v square is equal to 9 by 100. V square is equal to 9 by 100. Then v is equal to 3 by 10. V is equal to 3 by 10. So the finally the value of, here much space is there, v square is equal to 9 by 10. Sorry, v is equal to under root 9 by 100 is goes to 3 by 10, that is 0.3. What is the velocity of each particle? 0.3 meter per second. So that is the problems related to electrostatics potential energy.